All right, so today I'm going to talk about, the title of my talk is How I Won and Lost the Record for the Most Distant Galaxy, but the more important part is why you should care. So the image there is a pretty cool image that Rachel and I put together showing Austin in all of its glory with an image behind it. Does anybody know what that image is shown in the background? The Hubble Ultra Deep Field, very good. All right, how many telescopes do you see in this image? How many people think one? How many people think two? How many people think three? Three is correct. What is the third one? All right, there. And who said it? Somebody said it. GMT, yeah, the Giant Magellan Telescope, which we'll talk about at the end. That's a new telescope being built in Chile that the University of Texas is a founding partner in. Okay, so let's get the clicker going right. There we go. All right, so I am actually a time traveler. And actually tonight you are all going to be time travelers. And you might say, Steve, you're crazy. Time travel isn't real. It's sort of true, but we have a trick. And the trick is that light only travels at a certain speed. If you want to look at some object that's some distance away from you, it takes light time to travel to your eyes, okay? So if you were to go outside and look out the sun, don't look at the sun, but if you looked at the sun, how long would it take that light to get to your eyes? And you had 8 minutes. You guys did much better than the group of high schoolers I asked that to last week. All right, so 8 minutes. Okay, very good. So the sun, I did not give them beer. I don't know if that's what you said. The sun is 8 light minutes away from us. Okay, so what about the nearest star system? How long does it take light to get from that to us? 4 years. Yeah, about 4 years. Yeah, we don't need decimal points, but thank you. So about 4 years. It's Alpha Centauri system. It's 4 light years away. So when we look at that star in the sky, you can't see it from here. You have to be in the southern hemisphere. You're seeing it as it was 4 years ago. Okay, not a lot happens on 4-year timescales, at least outside of the Earth. So we'll take another step back and think about the Andromeda galaxy. It's the nearest large galaxy in the sky. How long ago are we seeing that galaxy? What's the light travel time? Yeah, about 2 million years. And so when you go look at that galaxy with your eye or your telescope, you can see it with your eye, you're seeing it as it is not today, not when you're looking at it, but as it was 2 million years ago, okay? And that is something that's extremely, extremely close to us. 2 million light years is nothing in astronomical terms, okay? And it's actually 2 million years isn't really anything in terms of astronomical timescales, but the most massive stars in the universe, stars 100 times the mass of our sun, do die on about million-year timescales. And so if you go and you look at that galaxy and you find the biggest, brightest, bluest stars, those stars likely don't exist anymore. So you're seeing light from something hitting your eyeball that's not there. Okay, so that's the key concept behind time travel. We're going to take it an enormous leap forward, and we're going to go look at all these tiny little specks and dots in this image. These things aren't millions of light years away. They're billions of light years away, billions with a B. And so we are seeing them as they were billions of years ago. And that's a big deal because how old is the universe? Yeah, all right, here we'll use the decimal point, 13.82 billion years old. That's our best guess. We know that pretty well from a variety of measurements. So 13.82 billion years. So if we can look billions of years back into the past, we are actually seeing a good chunk of the way back towards the beginning of time. And so we can really see how galaxies form and evolve. So that's the introduction to what we're going to talk about today. All right, so what do I study? I study how galaxies evolve. I would call myself a galaxy evolutionist, the not as controversial type of evolutionist. And so we are finding galaxies, tiny bits in the early universe, and we want to know, how do you go from those tiny little bits we saw in that previous slide to the Milky Way, which is big and glorious and complex, okay? And this is really the ultimate origin story, okay? So not how did humans come to be, not how did even the Earth or the sun come to be, but how did our galaxy come to be? Our galaxy hosts our sun, it hosts the Earth, and it hosts all of us and all of our beer, and so we want to know how that came to be, okay? So that is why I do it. That is how I convince people it's interesting and worth doing. I'm not inventing self-driving cars. I'm not curing cancer, but I like to think there's at least a small, tiny place in there for non-directly practical research to learn about where we came from. All right. So a key question, if you didn't know, what is a galaxy? If you've never learned about galaxies before, you don't know what the hell I'm talking about. So what is a galaxy? Well, this is a galaxy. Does anybody know what galaxy this is? Andromeda. It looks a lot like the Milky Way. Do we have pictures of the Milky Way that look like this? No, why not? We're in it, right? We're in it. You might say, well, let's just fire a camera straight up out of the Milky Way, have it turn around and take a picture. Right, a selfie. We'd call it the selfie project. That would go over really well in Congress, I'm sure. That would take a long time, okay? I should have done this, but let's see if we can do it really quick. So the New Horizons space probe, which has been in the news, the one that just went to Pluto, it's the fastest thing we've ever sent into space. It would take about, 20 million years to go 1,000 light years. And so say getting 1,000 light years, that's about the width of our galaxy. So we want to get 10 times that high to take a good picture. So we'd have to go 200,000 years, and we'd have to take a picture, and it would have to send that picture back, and that would take a couple more thousand years for that picture to get back. So we're talking a long, long time from now. So no, we don't have those pictures. This is the Andromeda Galaxy, not as it is today, but as it was how long ago? 2 million years ago. So maybe some of those, these big bright blue things aren't there anymore. Who knows? So that's a galaxy. Okay, this is also a galaxy. Sombrero, I don't even have to ask. Yeah, the Sombrero Galaxy looks a little bit different. It's not that much different than if you took Andromeda and put it directly edge on. It wouldn't look all that different from the Sombrero. This is also a galaxy. This is an elliptical galaxy. We call these red and dead galaxies. It just kind of looks like a big red, yellowish, orange ball of stars. Okay, blue stars are nice and young. Red stars are old and cold and dead. And so when we see a galaxy that's all red, that means it has no young, massive stars. Okay, so that galaxy's been sitting there for a while, hasn't been doing too much. There are a lot of those these days. And then this is another galaxy. Anybody know what this is? Nobody. Oh, close. +1. M82, there we go. This is M82, okay? So all of these are galaxies. They all look different, and understanding why they look different helps us figure out what's going on. M82 is spewing out tons of gas and dust. That's what this red light is. This is actually showing you where hydrogen gas is. It's forming so many stars in that center of that galaxy. They're putting out so much energy that they're blasting out gas from that galaxy. It's actually going to strangle itself. It will keep it from forming more stars. And so that's interesting. We actually think that process happens a lot, especially at early times. All right. These are also galaxies. I heard somebody say what it's called. The mice, yeah. So this is a pair of interacting galaxies. If you took two sombreros and threw them together, you would get something like this. That happens all the time as well. Galaxies merge. It's part of what changes galaxies. The Milky Way probably underwent a major merger like this at least once in its past. Okay. So that's galaxies today. They're big. They're spiral. They're elliptical. If we go back to early times, and remember, we don't actually need a time machine, we just need a big telescope, galaxies look very different. So this image is called, again, what's it called? The ultra deep field. You're forgetting a word at the beginning. Hubble ultra deep field. That was ingrained into me by a professor in graduate school. Don't let anybody forget that this image, the best image we have of the distant universe, was taken by the Hubble Space Telescope. Okay, so the Hubble ultra deep field, these boring kind of big bright things, those are nearby. This right here is actually a star in our galaxy. Here's another star in our galaxy. They're just in the way. This is a nearby galaxy. But most of those tiny faint bits are really, really far away. And if we zoomed in on those tiny faint bits, which we'll do, you'll see they don't look like spiral galaxies. They look very different. So why is that? And that is what this slide says. Why is that? That's the main goal that I'm trying to figure out with my research. How do you go from a universe filled with these, which is actually an artist's rendering, not a real galaxy, to a universe filled with these, things like our Milky Way or Andromeda, as shown here. So that's what we're trying to figure out. So we have a decent idea of how things started thanks to dark matter. Dark matter is sort of amazing because we have no idea what it is, but because it only interacts through gravity, we can model it extremely well. So this is an awesome movie from a computer simulation. I think it was run at Stanford. And it's showing what happens if you throw a bunch of particles into a box, dark matter particles, and press play and turn on gravity and see what happens. And you can see the universe has this amazing structure. We call it the cosmic web. You can see these filaments here, other filaments here, and where they interact, you have nodes, and it's where these nodes are where you get a lot of galaxies. So each of these bright bits, these are what we call dark matter halos. They're overdensities of dark matter. I'll say that again. And that's where galaxies are actually forming. Okay? And our observations back this up. And so we can basically play a movie of what the universe should look like structurally. We can get an image of the backbone of the universe. And all we have to do, us observers that are out there at the telescopes, is figure out what the gas and stars are doing. And the gas and stars are only 4% of all the energy density in the universe. So you would think that's easy. The problem is, gas and stars, they interact gravitationally, but they also interact with a variety of other forces. They have magnetohydrodynamics, which is a word you never want to say, especially not on a stage. It's really, really complicated. And so we need to do lots of observations to fill in these halos with the galaxies. And what is this telescope? Hubble, the Hubble Space Telescope. So if we want to see those really faint distant galaxies in the really distant universe, we need a state-of-the-art facility. Okay? When you need a new car and you say, I want state of the art, and you say, I want a state-of-the-art car, do you go buy a 1990 car or do you go buy a 2015 car? A 2015 car. What if a 2015 car would have cost you a few $1 billion? Maybe you'd figure out how to make the 1990 car run a bit better, right? Okay. So those of you who know anything about Hubble know where I'm going with this. Hubble is 25 years old. This year is its birthday. It's its 25th anniversary. The reason why it's so great, well, it's two reasons. Number one, it's above the atmosphere. The atmosphere is good. It helps us breathe. We like the atmosphere. But it blurs things out. It can both block light and scatter light, and it can also wiggle light around. And so it blocks some light you want to see, and it blurs out your images. So you get above the atmosphere no matter what kind of telescope you put up there and you're gaining. All right, the second thing is we fixed Hubble several times. The most recent time being in 2009 when astronauts went up and repaired one camera and put in 2 new cameras, one of which has made possible all the research that I'm going to be talking about. And so Hubble, even though it's 25 years old, is really state-of-the-art. Does anybody know how big the mirror is on Hubble? The diameter of the primary mirror, which is the single number you need to know about telescopes. Yeah, right. So about 2.5 meters, 2.4 meters. And so a good analogy I use, that's about the height of your average NBA center. Seems tall, right? Depends on the team who you're a fan of. But it's not actually that tall. If you think about the biggest telescopes in the world, the Hobby-Eberly telescope in West Texas, the Keck telescopes on Mauna Kea in Hawaii, they're 10 meters in diameter. They have a much larger light gathering power, but they have the atmosphere to deal with. And so these telescopes are very complementary. So the 10-meter telescopes on the ground do not make Hubble irrelevant. They both have their place, and we do need them both. All right. So we've talked about time travel. We've talked about we want to really find distant galaxies. We've talked about now we have the tools. We have the Hubble Space Telescope. But how do we know which of those galaxies in the image are far away and which ones of them are close? Okay. For that, we have to give thanks to the actual Hubble, the guy Hubble, Edwin Hubble, who wrote a awesome paper. I wish I could write a paper this good. In 1926, I think, discovering that the universe was expanding. Okay. That is very key for everything that we do in astronomy now, or at least in galaxies, all right? So how did he do that? Well, it was known at that time that there was a certain class of stars called Cepheid variables. These stars pulsate. They get bigger and smaller and bigger and smaller. And as they pulsate, they get brighter and dimmer and brighter and dimmer. And the ones that are intrinsically brighter pulsate on longer time scales. And so if you can measure what is the typical time from peak brightness down and then back to peak brightness, you can actually tell how intrinsically bright it is. And once you know how intrinsically bright it is, it's like somebody telling you, that's a 60-watt light bulb. Now tell me how far away you are by measuring how bright it is. So if you know how bright something is intrinsically, and you measure how bright it actually appears to you, you can actually measure the distance to that object. And that's exactly what Hubble did. This is the Hubble diagram from Hubble's paper, written by Hubble. And this is plotting the distance to a bunch of galaxies versus their velocity. He was measuring how fast the galaxies are moving towards or away from us. And you'll notice the distances are all positive, duh, because you can only be at a positive distance from us. But the velocities are also positive. And that means that all galaxies are moving away from us. Not only that, but the more distant galaxies were moving even quicker away from us. And that's exactly what you would expect if you had an expanding universe. You might say, right, I just told you how he measured the distance. How did he measure the velocity? And he did that using the Doppler effect. And you've all experienced the Doppler effect, probably not with light, but with sound. If something is moving towards or away from you and emitting a wave, be it a light wave or a sound wave, the wavelength of that wave changes. And so if I turned on one, this is a laser, say I turn on a flashlight, and I ran towards you really quickly, like a good fraction of the speed of light, that light would actually start to look bluer to you because the light waves are getting compressed, and that makes them look bluer. If I was running away from you really quickly, the light waves get stretched, and they would start to look redder, okay? And that's what's happening in the universe. Everything's moving away from us. Everything looks redder than it should. The more distant things look even redder. That's the basic concept behind what we call redshift. Okay? And because more distant things are moving more quickly, all we have to do is measure these velocities, and that actually gives us a distance. If all I know is the velocity, I can go to this little best fit line here, and that can tell me the distance. Okay? So it turned out Hubble was off by about a factor of 6 or 7 for a variety of effects, but we have a much more well-calibrated Hubble law now. We know what this line is. And combining that with some cosmology, we can come up with this legend, which we're going to use for the rest of today. Redshift, that is basically a distance to an object. where we measure how redshifted its light is, and we can turn that into a distance. Okay, redshift 0 is today, and today we are about 13.8 billion years since the Big Bang. If we go out to a redshift of 1, it doesn't sound like that much, but at redshift 1, you're already 6 billion years since the Big Bang. You're already more than halfway back in the history of the universe. And I am here to tell you that redshift 1 is boring. That last half of the history of the universe, almost nothing happened, okay? We've learned that. There was a time when that was great. Apologies towards some of my senior colleagues in the room. There's lots more to learn, trust me. But there's a lot of discoveries to be made out at higher redshift. And so this is our legend. We'll go all the way out to a redshift of about 7.5 today. That's not an accident. I'll show you why. And at a redshift of 7.5, I will show you a galaxy that is from that time. We're seeing it as it was 0.7 billion years or 700 million years after the Big Bang. So we've gone back about 95% of the way in the history of the universe, and we can find galaxies, and we can measure their distances, and we can know for certain that that's where they're coming from. All right, so that's redshift. Okay, so how do we find distant galaxies? We look for things that are really red. It's slightly more complicated, but not really. Okay, it's really easy. All right, so let's travel through time. I told you I was a time traveler. You're all going to be time travelers. So we're going to zoom in on the Hubble Ultra Deep Field. We've traveled through time an amazing amount. We've traveled 5 billion years back in time. Now we're 8.5 billion years from the Big Bang. This is a redshift of 0.5. What kind of galaxy does this galaxy look like? It's a spiral, right? It doesn't look that much like our Milky Way, so we don't care. We're going to move on. We want to go further back in time. We want to find those little bits. We want to find the little bits, all right? So keep an eye out for the little bits. There's lots of little bits, but I've measured the distances to all of these little bits, and here's one. Now we are at a redshift of 4, so now it's getting interesting. Now we're only 1.5 billion years from the Big Bang. Does this look like the Milky Way? No, it looks like, what do you think it looks like? It's like cloud shapes, right? I don't know, a clump. 2 clumps. Okay, it's not terribly interesting. What color would you say it is? Reddish, maybe yellowish. Okay, that means something interesting. I'll tell you in a minute. I'll keep you in suspense. Let's play one more movie. We'll jump back another 600 million years in time, I think, if I remember correctly, to a time only 900 million years after the Big Bang. And we see another thing that also looks like a clump or 2 clumps. All right? This is at a redshift of 6. Until Hubble was serviced in 2009, we could not see further than a redshift of 6 because beyond that distance, all of the light from these galaxies gets redshifted into the near infrared where our eyes cannot see and where Hubble could not see, at least not very well. One of the things the astronauts did was install a brand new awesome near infrared camera called the Wide Field Camera 3 that allowed us to go to greater distances. But one point I want to make here, what color is that galaxy? Blue, good audience. So I didn't show you all the galaxies, I only showed you 2, but at redshift 4, galaxies tend to be red, and at redshift 6, galaxies tend to be blue, okay? That's telling us something about chemical elements in galaxies, all right? When the universe was born in the Big Bang, only hydrogen and helium existed. There were no heavy elements, which astronomers called metals, no oxygen, no carbon, no iron, no gold, none of that stuff, right? That was all formed in stars, and that took time for stars to form those heavy elements. As galaxies enrich themselves with these elements, they tend to look redder. And so what we're seeing is that at a redshift of 6, a decent time after the Big Bang, but not a lot, about 1 billion years, galaxies didn't have any of these heavier chemical elements. 600 million years later, by redshift of 4, they did. So we're actually finding that time when those heavy elements were building up for the first time. What's really cool about this is you need those elements to make planets. This galaxy probably doesn't have any planets because there were no heavy elements that you need to make things like all the stuff that we stand on here, right? But by redshift 4, it was there. And so this is really the epoch of planet formation, if I'm really going to stretch things a little bit. All right. So I told you I measured the distance to every single galaxy in that image. I lied a bit. I made a guess, a very well-educated guess, but just a guess at how far away they are, basically by how red they look. But we want to measure precise distances, maybe not for every galaxy, but at least for enough of them that we know we're not fooling ourselves. And the way we do that is with spectroscopy. Raise your hand if you've heard of spectroscopy before. All right, good audience. So spectroscopy is the power behind astronomy. That's when we go from being astronomers to being astrophysicists, because it tells us about all kinds of processes that are happening in these galaxies. And the one-sentence explanation about spectroscopy is it basically lets you take the light from a source and split it up into its component colors. And you can learn about things. Particular atoms show particular features in a spectrum. And they're all unique. So if you see these 2 lines there, you know sodium's in that galaxy. If you see these 2 lines here, you know calcium's in that galaxy. And if you see these 2 calcium lines, but they're shifted a little bit to the red, you would, or I guess to the red is this way on the left, you would say, ah, that's calcium and it's redshifted by a bit, so I know it's a little bit far away from me. It's in the expanding universe. For the galaxies I'm looking at, I'm going to use this thing here. So this is the fingerprint of the galaxies I'm looking at. The distant universe, these galaxies are all forming lots of stars. When they form lots of stars, they put out lots and lots of highly energetic light. That energetic light makes this big spike here. This big spike comes from the very exotic atom known as, any guesses? Hydrogen. All right, I was being sarcastic. Hydrogen is the most abundant atom in the universe. That's why we know it's going to be there. This is called the Lyman alpha line of hydrogen. Dr. Livermore made me promise I was going to explain what LAE meant. LAE stands for Lyman alpha emitting galaxy. So it's a galaxy that you find because it has a strong Lyman alpha line. Okay, so we know these galaxies should have this line, so we want to take the light from these galaxies, put them through a prism, spread them out, and look for this spike. And if we measure the precise wavelength of this spike, that tells us the precise redshift to that galaxy. All right, to do that, we need big glass. You can do it with Hubble, but it's really, really hard. You can actually do it a lot easier with Keck. These are the Keck telescopes on the summit of Mauna Kea in Hawaii at the enormous altitude of 13,500 feet, which sounds a lot right now, but will not sound very much when we learn about Sophia, that flies a lot higher. Next. But what's cool about these telescopes, in particular one of them, Keck 1, which I don't know, Tapped, which one is Keck 1, the left or the right?
Our right.
All right, okay, this is the Keck 1 telescope here. Keck 1 has a brand new instrument called MOSFIRE, which is this awesome near-infrared spectrograph that allows us not just to look at one galaxy and take a spectrum, but allows us to look at 45 galaxies and take a spectrum. And when you're looking at really far away things, you need to stare at them for an entire night. And they would not give me time if I said, I want to use this telescope, which costs $110,000 a night to run, to stare at one galaxy. If I tell them I'm going to stare at 40 galaxies, they'll be like, oh, okay, I guess we'll let you do it for one night, maybe two. All right, so we went to Keck. This was an image from us at Keck the first time we tried to do this in April of 2 years ago with Mimi Song, who's a graduate student here, and Vithal Tilvi, who's a postdoc at Texas A&M, but now he's at Arizona State, so he's okay. All right, and here's one galaxy. I told you we looked at 40, and we did look at 40, and we only saw one, and that's because this is really, 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 really hard, okay? But we did see one galaxy. What color is this galaxy? It's red. So we haven't taken the red shifting out of this one. This is red because it's at very, very, very high redshift, okay? So here is its spectrum, and it is beautiful, all right? Does it look anything like that fingerprint I showed you? No, because it's filled with noise. But there's a tiny little bit of signal in there that I've highlighted just for you and for all of my readers by this red line here. This is that Lyman alpha line. And you might say, how do you know it's a Lyman alpha line? And I would say, read the damn paper, but I can tell you off stage because I know I'm going long. I spent about 3 or 4 months of my life trying to convince first myself, then my collaborators, then the referee, and finally the rest of the world that it is in fact Lyman alpha at the nice redshift of 7.51, which at that time made it the most distant galaxy known. All right, so there it is. This is that, I promise. All right, so we wrote a paper in the journal Nature where we talked not just about how far away it was, but about the fact that it's forming an enormous amount of stars, which is a whole talk in itself. These galaxies are super interesting. We're learning a ton about what's going on. And you guys all liked this. And so we did a press release, thanks to the help of Magellan Observatory, the press office. And it spawned 300 internet articles. We were able to track the web views, and 150 million people, or at least unique people, clicked on this article. So that was crazy. It was the second most read story on the BBC that day because there was a horrible murder in the UK. That was the first read story. We were the second read story. And best of all, there is a painting of an artist rendering of it in a sewer tunnel in Victoria, BC, which somebody emailed me. It's actually part of this whole project, the history of the universe, and so they chose our galaxy to highlight that. All right. So where do we stand now? So I held the record for a whopping 18 months, which is actually pretty long in this game. The addition of MOSFIRE, that instrument to Keck, has really started an arms race for breaking these records. And so our record was recently broken by an astronomer named Pascal Louche, who's at Yale University. And here's his spectrum here. This is the same thing. This is Lyman alpha. He is at a redshift of 7.73. And so we were sad, but we knew it was going to happen. We were hoping to break it ourselves. And we probably actually have. We have a lot of data on our computers that we just need to publish that probably is at a higher redshift than this. But oh well, we didn't get there. So Pascal broke our record. He even got a mention on Saturday Night Live. And so second most read article on the BBC, and sewer tunnels are cool, but they actually talked about his on Saturday Night Live, which is pretty cool. And so what does this mean? Okay, so we broke the record at redshift 7.5. At a redshift of 7.5, here's our awesome timeline. Here we are today. Here's the Big Bang. At redshift 7.51, we are seeing 94.9% of the way back to the Big Bang. Now you ask, what new glories have we seen by moving the frontier out to redshift 7.73? There it is. 95.1% of the way back to the beginning of the universe. We've cracked the 95% barrier. All right, I'm being a little sarcastic. It is a big deal. It's a slightly small stepping stone, but in fact, I haven't added it here. But there is a paper that's out there now that claims a Lyman alpha line at redshift 8.68, which would bring us back 96% of the way back. And so technology is really driving our ability to see these objects. All right, so what's next? I'm just going to show you some of this other data that Dr. Livermore and I have sitting on our computers that someday we'll share with the rest of the world. Here's one at 7.55 that's nice. Here's one at 7.06, one at 7.60, and one at 7.78 that if we had gotten out there, we would have kept the record for at least a little bit until the more recent one came out. This one's a little dubious, so we need to look at it a bit more. All right, I'm going to skip this. New imaging is great, but I like to talk about telescopes. Telescopes are my favorite thing. I love to go there. I love to talk about them. I love to talk about future telescopes especially. So what is the future in space? So this is, again, a movie of dark matter and galaxies. And the thing I didn't tell you before is that when we take the deepest image with the Hubble Space Telescope, all we are seeing is this one big bright thing there. We can't see all those tiny little faint bits. And that's because, as glorious as this 2.4 meter telescope is, it's simply not big enough. And so we need to put a bigger telescope in space. And we will in a little over 3 years' time. What is this? The James Webb Space Telescope. How many of you saw the full-scale model when it was in Austin 2 years ago? Yeah, so it's a big telescope. The mirror is 6.5 meters in diameter. It's 7 times the light-gathering power of Hubble. So Hubble will only see the big bright thing. James Webb will see all of those galaxies in the cosmic web. It will be immensely powerful. And to give you an example of this, we'll go back to our favorite image, the Hubble Ultra Deep Field. What would happen if we looked at this with JWST? And in 3 years or 4 years, I'll be able to show you. But for now, we use a computer to guess at what it's going to look like. And one thing I want you to notice, you notice how you can see lots of just blank space between the galaxies? Okay? Watch what happens when we show a simulated JWST image. Okay? It's now filled with galaxies. It's really hard to find a blank region here. And that's because the Webb isn't just seeing the tip of the iceberg, it's seeing the whole dang thing, the whole iceberg. So how are we going to learn about those galaxies? For that, we need telescopes on the ground. Just like we're now using the Keck telescopes to follow up galaxies we find with Hubble, we are going to use the giant Magellan Telescope shown here to follow up galaxies that we find with JWST. This telescope from end to end is 25 meters. It's enormous. It's going to have about 5 times the light gathering power of Keck, and it's going to allow us to learn a lot more about the galaxies we can see now and to learn a lot about the galaxies that we're going to find with the Webb. And best of all, being at the University of Texas, we have a 10% share of that telescope. That means we get about a month of observing time every single year. And so I look very much forward to my guaranteed 2 or 3 nights a year. I think I'm staring at our director over here. Guaranteed, I think he says, right? As long as I write good proposals. So UT is one of 10-ish partners now. We're all, for the most part, universities. The government is not involved in this project, at least not at this point. And so the University of Texas has generously given us about $50 million towards this project, which we have paid. We are trying to raise another $50 million. You probably won't fit that in the tip jar, but if you are independently wealthy, just come talk to me. I'll point you to the right person. We're trying to raise that to get our share up to 10%. Texas A&M is also a founding partner. Harvard, Arizona, Carnegie Observatories, a lot of the great institutions in our country. All right, and so that's all I have. Thank you, and yeah.
All right, we have time for questions for the Notorious L.A.E. Straight back.
Yeah. Yes. So I heard half of what you said. So I think you're asking about basically the light that we're actually seeing in these images. And so these really distant galaxies that we're looking at in the near infrared, that's the wavelengths of light that we're observing, we are actually seeing their ultraviolet light. So it's light bluer than our eyes can see, have redshifted all the way through the optical, all the way into the near infrared. And in fact, these galaxies beyond a redshift of 7 or so are literally invisible. There is no visible light reaching our Earth from these galaxies. And so you have to see them in the near infrared.
Right up front.
Have we ever seen nebulous stars with any telescopes?
Nucleus stars?
I can't really pronounce it, but it's where 2 stars E and it's
Yeah, so
the sun and what they mean.
yeah, so the question was, so do we ever see stars merging? I don't know if we've ever actually caught stars in the act of actually right at that last second, but we definitely do see binary stars where one star is orbiting around the other, and a lot of times the massive one will suck off the material from the other one, and it can create some pretty cool fireworks. So absolutely, yeah, good question.
All right, another question here. Right down here.
Where's that new telescope going in?
It is going in the foothills of the Andes in Chile, which is one of the 2 or 3 best sites on Earth for telescopes.
Is something that somebody can go up to and walk up to and visit?
Probably not. I don't know if they're going to do tours. That's a good question. We'll think about it. I don't know. Yes. If you donate $50 million, yes, I guarantee it.
Because of the accelerating expansion of the universe, what point will these types of measures that you do become untenable entirely because it's no.
Yeah, that's a good question. So eventually...
Repeat the question, please.
Oh, sorry. Yes, thank you. At what point can we just not see any galaxies because of the expansion of the universe? I don't know the answer to that question, but it will happen. Basically, anything that is gravitationally bound to our local group, which is the Milky Way and Andromeda and some smaller galaxies, will eventually fall in and will all form some giant galaxy, which people have actually called, I think, Milkomedia or Milkomeda or something, Milky Way Andromeda. So Milky Way and Andromeda will merge in about 4 billion years. All the other things will fall in. Everything else will keep moving away. The universe's expansion will accelerate to the point that it's faster than the speed of light and we can't actually see them. When that will be, I don't know. Several, many billions of years from now, and I will not have to worry about how to observe. But people are thinking. There was a paper on Milkomedia that was, how will people learn cosmology? And I don't remember the exact reason what they figured out, but they will be able to figure out the cosmology of the universe by studying how hypervelocity stars orbit, really fast stars orbit in that galaxy.
All right, one more question, straight in the middle here.
So what's the Z value for the Big Bang itself?
Infinite. What is the z-value for the Big Bang itself? Infinite. There is no z-value. I will answer a different question that I know the answer to, because I like to do that. What is the redshift? I'm going to make it up. What is the redshift where we think the first galaxies formed? And we think that is probably somewhere between a redshift of 12 and 15. And that is a redshift that we can actually look at with the James Webb Space Telescope. Not only is it big, it's very sensitive in the infrared where we can see these galaxies. So stay tuned. It launches in October of 2018.
All right, let's thank Notorious L.A.E. one more time.